All right, so let's look at the binomial theorem, and we're going to look at the binomial expansion theorem as well as finding a specific term from a binomial expansion. But before we get into that, there was a French mathematician, Pascal, who described an array of numbers corresponding to the number of ways R elements are chosen from a set of n objects using the NCR notation. Now, Pascal's triangle with numbers looks like this. First number is a 1, and then the next row down is just 1 and a 1. The next row down, all we do for Pascal's triangle is add these two numbers together. The middle number will become a 2, and then we have a 1. And Pascal's triangle just continues that pattern of a 1 at the beginning and 1 at the end, adding the two values. 1 plus 2 is 3, 2 plus 1 is 3, and then we end with a 1, and that pattern continues. So Pascal's triangle, this array of numbers. But what this corresponds to is if we set it up with combinations, the first number we could say is 0C0. The next one is 1C0, 1C1. If you put these numbers in your calculator, you'll find out that all of those equal 1. The next row is 2C0, 2C1, and if you check 2C1, it corresponds to the number 2, and then 2C2, and that pattern continues. And again, you might think, well, oh, okay, what does that mean? Well, this is what we are going to learn and use about Pascal's triangle. What we're going to consider with Pascal's triangle is that the top of the triangle is the 0th row. Now that might seem a little bit strange, but that'll come into play in a second here. That's the 0th row. This is where n equals 0, corresponding to that 0 in your NCR. Now the first place, the 1, corresponding to that first number in each row, we consider that the 0th place, where R is 0. So that first value is in the 0 row, n is 0, in the 0 position where R is 0. Now from that notation, every number that corresponds to the first number is the 0 position. The next one down would be the 1 position and the 2 position, etc. So Pascal's triangle, we're going to use that, but the important thing to note here is the position and where the numbers come from in NCR. So let's put this together, and we'll put it all together. So let's put this together to make it a little bit clearer in how we're going to use it. Well, here is a binomial, x plus y to the 0. And if we were to expand this binomial, we know that anything to the 0 would just be 1. Next one down, x plus y to the 1, well, it's just x plus y. If we squared this, we've done a lot of quadratics, we get x squared plus 2xy plus y squared, and you could take your time and you could cube it, and it does take a little bit of work, but the cube of x plus y squared is x cubed plus 3x squared y plus 3x y squared plus y cubed. And remember, when we're expanding a binomial, x plus y cubed is really just x plus y times x plus y times x plus y, all distributed, multiplied together, and expanded in. Well, let's look at the coefficients. And what I'm going to do is I'm going to put the numbers 1 in there for any of those variables that don't have a written coefficient, because we want to look at the pattern of these coefficients. Now, all we have changed in the expressions are the exponents. We went from 0, 1, 2, 3. Well, what about the coefficients? First coefficient is 1, only one coefficient. Next time, we have a 1 and a 1. Well, the next coefficients are 1, 2, 3. I hope you see a pattern at this point. The next coefficients are 1, 3, 3, 1. And if you look back at Pascal's triangle, you'll see that those correspond to the rows in Pascal's triangle, which means we could write those rows with our NCR notation from Pascal's triangle, which means in this form, 1 we could write as 0C0. That is the first row, or the 0th row, where n is 0. 1C0, 1C1. Remember, the first position is the 0 position. The next one, 2C0, 2C1, 2C2, giving us 3 terms. 3C0, 3C1, 3C2, and 3C3. Now we could continue this pattern of expanding because we know that the next row down will be 4C0, 4C1, 4C2, 4C3, and 4C4. So if we want to expand x plus y to the 4, and using that NCR for the coefficients, we know that x plus y to the 4, the coefficient, well, the first coefficient is going to be 4C0. The next one will be 4C1, 4C2, 4C3, and 4C4. Now that's just the coefficients. We want to look back and see what are the pattern on the variables. Well, let's compare the exponents. If we look at the exponent on the variables, let's look at the squared one. It starts with a 2 on the x. As we work our way down, it's not written, but there's a 1 on the x. There's also a 1 on the y. And if we work our way down, we have no x term. Now, what's not written is the corresponding y and x term in this expression. We want x and y to disappear when we're doing x squared. We want the y to disappear. We want y squared. We want the x to disappear. So the exponent we put on them is 0. And what we can now see is we have a pattern of numbers. The x value starts at 2 and works its way down to 1, 0. The y value starts at 0 and works its way up 0, 1, 2. So if we were to put an x, y for each of these coefficients, I'm just going to put a plus sign as well. We'll take care of the exponents in a second. We're going to see a pattern here for our variables. Well, if we continue the pattern, the x's start at 4, corresponding to 4, and working their way down. So we get 4, 3, 2, 1, 0, and the y's start at 0 and work their way up to 4. 0, 1, 2, 3, 4. Now, it looks a little messy right now, but what this allows us to do is actually do an expansion of a binomial with a high degree relatively quickly. 4C0 is 1, x to the 4, y to the 0 is just 1, so it's going to disappear, plus 4C1 is 4, x cubed, y to the 1, we don't need to write the 1 in. 4C2 is 6, x squared, y squared. 4C3 is 4, x, y cubed, plus 4c4 is 1 y to the 4. And there's our binomial expanded in 2 steps. Now we can go 1 step further and get rid of the 1's, like so, and there is our expanded binomial. And it's a very quick way to expand a binomial with high degrees. It's just following that pattern. And that pattern is really just a formula called the binomial expansion theorem. And the binomial expansion theorem is really just a way of expanding any binomial if it's in the form a plus b to the n, where n is a positive integer, and we use this equation. Now, you may not have seen this summation notation before, and what this summation notation tells us is our r value is going to start at 0 and work its way up to whatever the n is. So if we were to expand this using that notation, it's just a compact notation, our first value would be nc. Our r is going to start at 0. The a value would have an exponent of n minus 0, which in this case would be 0, times b, and I'll write it in just so it's clear, to the 0. Now the summation means we're going to add. The next term will be nc. Our r goes up by 1 value. A then would be n minus 1, because our new r value is 1, times b to the 1. Plus, and I'm going to do it below here, plus the next one would be nc2, a to the n minus 2 times b squared. And notice the r just keeps going up. And we would just keep that pattern going until we got to the point where n was equal to r. We eventually work our way up to the ncn. That would mean we'd have a to the n minus n, which of course is 0, times b to the n. So it's just this formula. Now, that formula seems a little bit complex, but once you do a couple of examples, you'll see how powerful of a formula this really can be. All we have to determine is what is a, what is b, what is n. So let's try an example. Expand 3x minus 2y to the 5th. Well, to expand it, we're going to use our binomial expansion theorem, where a is 3x, b is negative 2y, and it's important we have that negative, and n is 5. So let's do our expansion here, and we're going to use our binomial expansion theorem. Our n is given to us. R is eventually going to work its way up to 5. So if we were to expand this, it's 5c0. The a value in this case, and I'm going to use brackets so it's clear, is 3x to the exponent 5 times, and I'm going to put this in again so we're clear, 2y to the 0. And we just follow that pattern by changing the r value each time and then adding them. The next one will be 5c1. The 3x will now be to the 4, and the negative 2y will now be to the 1. Next term, 5c2. It'll be 3x cubed times negative 2y squared plus 5c3, 3x to the 2, and negative 2y to the 3. We're almost there. Plus 5c4, 3x to the 1, negative 2y to the 4, plus 5c5, 3x, and again, now we're at n equal to r, so the 3x is to the 0, and the negative 2y is to the 5th. Now again, this might seem like a lot of work, but if you can imagine having to expand 5 of these brackets out and do all the math, this is a much quicker method. So let's go through and figure out each of these numbers. Well, 5c0 is 1. 3x to the 5th, well, we have to put everything to the 5th. So 3 to the 5th is 243, and x to the 5th would just be x to the 5, multiplied by negative 2y to the 0. Just to be clear, I'm going to put that in as 1. See if you can pause the video and figure out the rest of those values. So there it is with the NCRs all expanded out, as well as all the exponents taken care of. Now the last thing what we have to do is just multiply out those numbers and get the final coefficient. If it's negative, it'll come out negative. If it's positive, it'll come out positive. Again, pause the video, see if you can get your final solution. And provided you've done all your calculations correct, there is our final solution, the expanded form of the binomial. Now again, it seems like a lot of work to expand out that binomial using the formula, but if you can imagine the amount of time it would take to multiply 5 brackets out and combine all the like terms, it's a much quicker way to find that expanded binomial. Well, we may have to find the entire binomial like we did, but we may also just have to find a specific term in the binomial. So we might not be concerned about the entire binomial, just a term. Then we can use this term equation. And you might recognize that the term equation is just one piece of the expansion. We want a specific term given the r, the n, the a, and the b. So let's use that equation to find the 6th term in this expansion. Well, when we need a single term, we want to use the term equation. There's our term equation, and what we have to do is just get our a, b, r, and n out of the binomial. Well, pretty straightforward to start. N is always the exponent, which is 9. A in this case is the first value, which is 2x. The b is negative 3. And the r, well, this is where we have to be careful. We're trying to find the 6th term. But if we look at the equation, the number is r plus 1. 6 is equal to r plus 1. So our r value is actually a 5. So you just have to be careful of the term equation. R corresponds to 1 below the term you're trying to find. Now that we have all that information, just plug it into the formula. N is 9. We want the r to be 5. A in this case is 2x. N minus r, let's just put it in. We'll get 9 minus 5 multiplied by b in this case is negative 3 to the 5. And at this point, we're done with the equation. Now we just have to find each of those numbers. Well, 9c5 is 126. 2x to the 9 minus 5, well, 9 minus 5 is 4. So this would actually become 16x to the 4. And negative 3 to the 5 is negative 243. Well, now that we've expanded each of the numbers, just multiply them all together, and we know we're going to be left with an x to the 4 and a really big coefficient, which is negative 489,888. A much, much quicker way to find a specific term in the expansion. And we're going to do more examples using this term equation and applying it in different situations in class.